We're going to continue with our analysis of a BJT common emitter amplifier in this video. In this example, remember that the beta spec we used was 100. Again, this would be found on the data sheet of the BJT. And we already found the Q values. Q values are what the base current, collector current, and output voltage are due to the DC sources only. So when we came up with these values, we ignored what was in red. We ignored the AC signal along with this capacitor. So now we're going to continue where we do consider the effect of this AC source. And remember again, the big picture is that this is the signal that we wish to amplify. Okay, this VI of 50, and this is actually millivolts here. Okay, so put a milli in there. This 50 sine omega t millivolts, this is the signal that we want to amplify. And in order to do that, we have the transistor that has the ability to amplify, as we discussed in a previous video, and we're supplying the DC energy to power that transistor to amplify this AC signal. So, you know, the big picture is we're going to get a bigger amplitude AC signal here at V out compared to what we have as our V in, and we don't get that amplification of the AC signal for nothing. The cost is the DC energy that we supply to the transistor circuit to power the transistor. Okay, so now before we get into any heavy analysis here, I just want to explain the purpose of the capacitor. The capacitor is called a coupling capacitor. And to see what its purpose is, you have to recall from your circuit theory that impedance of a capacitor is just minus J 1 over omega C. And to explain the purpose of a coupling capacitor, you just look at the magnitude of the impedance. So we're just looking at 1 over omega C. Remember omega, this is your frequency, your source frequency. So coupling capacitors, or any type of capacitor, but when a capacitor is used in this way, it's called a coupling capacitor. For DC, omega is equal to 0, right? Because with the DC source, you don't have any sort of oscillation. So the impedance of the capacitor, the magnitude, is just going to be 1 over 0, okay, which is infinite. So to DC current, a capacitor just acts like an open. Now for AC, omega is going to be something other than 0, because AC sources, you do get an oscillation, as you know. And if we make that source frequency times the capacitance, if we make that a big number, so if omega times capacitance is large, ideally if you make it infinity, well, now you're going to have 1 over a big number, ideally let's say infinity, well, that's 0. So a coupling capacitor, it blocks DC, okay, because it acts like an open to DC, and to AC, it allows it to pass through virtually unimpeded, because ideally it acts like a short. So what this means in our analysis is that when we add this AC source to our circuit, because we put this coupling capacitor in between the source and where we're connecting it to the circuit, it doesn't affect these Q values. It doesn't affect these DC values. These are going to be the same. What it does is that it introduces a sinusoidal variation around these Q values. Okay? So the Q value for IB that we obtained earlier, the 7.8 microamps, okay, that was obtained by doing a KVL around this loop here. And if you look back at the previous video, we ended up with 0.9 volts divided by 116K. Okay, and that's what gave us the 7.8 microamps. Well, now when we add that AC signal, which is going to cause a sinusoidal variation around this 7.8 microamps, the way we come up with what that sinusoidal variation is that we look at, well, the path for the AC is that, you know, you have a loop here, you have a loop here, but because over here in the emitter, where the emitter is, you got a 1K resistor, and over here where the base is, you have a 15K ohm resistor, most of the AC current is going to be in this path. So your total IB is just going to be your Q value plus, okay, added on to that, the AC part of the base current, which is going to be your 50 sine omega t millivolts. Okay, remember this is millivolts. Actually, let's put it in volts. So we'll write it like this. Okay, it'd be 0.05 volts, okay, which is 50 millivolts. So that's our AC voltage, and then divided by what will come out to be 101K, right? Because remember, the current through the emitter resistor here is your base current plus your collector current, and your collector current is equal to beta spec IB, and beta spec's 100, so you'd have 100 IB plus IB, which is 101 IB times 101K, which is 101K. So you see the denominator here will be 101K. Instead of when we did the base current for the Q value, which was this path that involved the 15K, it was the 101K plus the 15K. That's how we came up with 116K. Again, if you go back and you look in your, or look at the previous video, you'll see that. Okay, so you see there's a different number here because we're just considering the AC current in this loop here. So what you end up with, and let's go to the next page, is that you'll have your IB total. Okay, total here meaning the DC along with the AC component of the base current will be the Q value 7.8, and if you work out that ratio of the sinusoid divided by 101K, it comes out to 0.4995 sine omega t microamps. Okay, so when you consider the AC signal, you get a sinusoidal variation around that Q value. Again, the Q value came from just the DC effect of the DC sources. So if we were to plot this, right, time, right, here's IB total. You'd have a sinusoid centered around the Q value. So here's your 7.8. And again, this is microamps. Microamps. Okay, so you're going to have a sinusoid varying symmetrically, even though I didn't draw it that way, this is symmetrically around that center point of 7.8. So this positive peak here would be 7.8 plus 4.95, which is roughly, 8.3 microamps. And this bottom peak would just be 7.8 minus 0.495, which is roughly 7.3 microamps. So when that AC signal is introduced into the circuit, it causes a variation around the Q value for the base current. Now we'll continue in the next video with this analysis and see that the same type of thing is going to be true with collector current and also the V out voltage, that now we're going to get a sinusoidal variation around the Q values that we had calculated earlier.